speaker is here because of some special relationship to Alan. And in this case, our last talk is by a very distinguished German physicist, Martin Zirnbauer from Köln. And he has a long history of collaboration with Alan, and they have joint grants, not only that, joint papers. And so we're especially pleased that Professor Zirnbauer has agreed to come here today. And you see the title, and I think it has some relation to a joint work with Alan.
That's correct. So I'm glad to be here. Thanks for asking me. And I'm glad to hear that Alan is not done.
Yeah,
Not even here. Alan will keep going. That's good news. And we've heard about Alan's love for mathematics. I want to add one thing. Alan is not afraid. In particular, he's not afraid of speaking to physicists. And that was sort of the necessary condition for us to not just coexist, but actually collaborate and do some useful stuff in the context of the Sonderforschungsbereich that we shared for 12 years. Now, I'm a physicist, and I dare not speak about mathematics to mathematicians. So obviously, I'll speak about physics. I'll give it a shot and see whether I can say some few things that make some minimal sense to you. The quantum Hall effect, if it's not intelligible in any case, it is famous. It's one of the paradigms of physics of the last 30, 35 years. It's been an inspiration for experiment and theory. What is it? It takes place in a two-dimensional electron gas, which is formed at the interface between an insulating substrate and a semiconductor. It takes place at very low temperatures, 1 Kelvin or below, and in a strong magnetic field. And what happens is that if you drive a current through the system and the quantum Hall effect takes place, then what's observed is a voltage transverse to the system, unlike a normal resistor where the voltage would be along the direction of the current. Now, that's the peculiar thing. And moreover, this Hall resistance, which is the ratio of the Hall voltage relative to the driving current, is expressed in terms of the fundamental resistance quantum by 1 over a number, which in the simplest case is an integer, but it can also be a fraction. And speak of that fractional quantum Hall. Now, when the magnetic field is very strong, all of the charge carriers, these are the electrons, go into what is called the lowest lambda level. In mathematical language, that is the space of holomorphic sections of a complex line number. So higher lambda levels are non-holomorphic, the lowest lambda level is the holomorphic sections. There's some counting. The number of holomorphic sections or states in the lowest lambda level is computed by taking the total magnetic flux through the system and taking it in unit of the flux quantum. So that's the number of states. Now we put electrons in there, and the ratio of the number of electrons actually occupying the available states relative to the total number of available states is called the filling fraction. So number between 0 and 1. Now at a half, we're at a symmetry point. We speak of the half-filled lambda level. And now particle Hall symmetry, something that one expects and actually observes for observers like the conductivity. The conductivity at a filling fraction nu is equal to the conductivity at the conjugate filling fraction 1 minus nu. Now that symmetry is not exact, but it becomes exact in a certain limit. And if I was speaking to physicists, I would elaborate, but here let's just take that for granted and mention that this is not a new thing. Steve Gervin, 35 years ago, talked about this. Strangely enough, experiments testing this were done just recently. This is from March this year. So what do you see here? As a function of filling factor or filling fraction, what is plotted is this conductivity. And the experimental measurements are the black curves. The red curve is just an invention. It's actually nothing but the reflection of the data at the symmetry point. Yeah? So, at small field, 1.5 Tesla, the red curve, which is the reflection, differs quite strongly from the black curve. So particle Hall symmetry is not very good. It's somehow here, but here it's broken. But you increase the field and it gets better and better until you have almost perfect agreement. So that's what's expected. This particle Hall symmetry, invariance, and that mapping the filling fraction to its conjugate, nu to 1 minus nu, becomes a good symmetry in very large field. Now, you may ask, well, if Gervin predicted this 35 years ago, why did the experimentalists only measure now? Well, the answer is there was a theoretical work a few years ago by Son, who proposed a particle Hall symmetric theory of the half-filled non-order. That was an important theoretical impetus, and it got the experimentalists back to the drawing board, making these measurements and producing what I just showed you. So that's my preamble. Just to give you an example of a physics system that is of interest, in particular is of recent interest, and that falls in the category of particle Hall symmetry. Now, there will be some words about our joint work with Peter Heinzner and Alan Huckleberry, and I'll start at the beginning. We're dealing with quantum mechanics in the presence of symmetries. What's the symmetry in quantum mechanics? Well, states in quantum mechanics are complex lines or rays. This is written for physicists mostly. And a symmetry is a map from complex lines from states to states that preserves all the transition probabilities. So, inner products. According to Wigner, a symmetry in quantum mechanics always lifts from projective Hilbert space to the complex Hilbert space as an operator which is of one of two types. It's either unitary or anti-unitary. No other possibilities exist. That theorem goes back a long way, the 1930s. A modern proof was given relatively recently by Dan Fried. Quite a nice little proof. Needless to say, symmetries form a group. More importantly, symmetries for us are operations that commute with Hamiltonian. I very strongly emphasize this every time I talk to my physics colleagues, because my physics colleagues want to speak about chiral symmetries, an example being the massless Dirac operator, which anti-commutes with the so-called chirality operator, or gamma 5. In our setting, that's not a symmetry. So I emphasize this very strongly. It's probably lost on you, but every time I speak to my physics colleagues, I make a big point of this. So
no, it's not lost.
Huh?
Thanks for saying this. It's not lost.
All right, the story is, the theoretical story, past Wigner, starts with Dyson a long time ago. He had a group of symmetries acting on a Hilbert space, motivated by Wigner's theorem. The symmetries come as unitaries, and then there is the possibility for anti-unitaries. The unitaries form a normal subgroup. Then we assume, then initially we forget about G1. This comes into the game in a moment later. Initially we think about the unitaries. We assume that they are reductive, and then we can decompose the Hilbert space into isotypic components. Each isotypic component is lambda by lambda, which stands for an isomorphism class of representations. We fix a standard irreducible representation, and then the isotypic component is that representation with multiplicity. Now here's one thing that I hadn't appreciated before working with Alan. He explained to me that a good model for this multiplicity space is the space of equivariant, G0 equivariant homomorphism from the standard irreducible representation into this isotypic component. So that's something I learned to appreciate. That's the best model that you can make. And now, doing so, the unitary symmetries, they decompose, the Hamiltonians decompose. The symmetries act on the standard irrep by the representation. They are trivial by G0 equivariance on the multiplicity factor. The Hamiltonians, in contrast, by Schur's lemma, are trivial on the irrep, and then do something on the multiplicity space. And the name of the game is figure out something about these reduced Hamiltonians. Now, that's where G1 has to be brought in. We enter the anti-unitaries, fix some anti-unitary, conjugate the unitaries, and that gives you, for every fixed T, you get an automorphism. Now comes the second assumption in Dyson's work. Assume that there exists a distinguished T such that this automorphism is of order 2. Call that thing time reversal. In physics settings, often it is the quantum mechanical operation of reverse, the quantum mechanical implementation of the operation of reversing the time direction in the dynamics of the physical system. And you quickly figure out that by the associativity of the operator algebra and the complex antilinear nature, that there's only two possibilities. On every isotypic component, T must square to +1 or -1. Now, Dyson did something that we did not do, and I'm proud to say that we didn't do that, and I still think it was a good thing we didn't do that. We, in our work with Peter and Alan, we kept working over the complex numbers. Dyson did something else. He just went to the reals. Worked entirely over the real number field, and then there's a quick argument to see that there are 3 possibilities. That's the positive aspect of Dyson's choice. The Hamiltonians commute with all the symmetries. So it intertwines real G representations. If you now look at an irreducible one, then Schur's lemma tells you that such an intertwiner is either 0 or an isomorphism. No other possibilities exist. Now, because we are not over C, we are over R, the standard form of Schur's lemma, which is the only thing I learned, doesn't apply. So, but it's still true that an intertwiner is either 0 or an isomorphism, and the way it's expressed is that it's a real division algebra. No? Anything that's non-zero. So what is a division algebra? Associative algebra with the property that any element that's not 0 has an inverse. No? So the intertwiners are in a real division algebra, and then Frobenius understood there exist exactly 3 associative real division algebras: the real numbers, the complex numbers, and the real quaternions. So that leads to a trichotomy of possibilities for the Hamiltonian. These then are the Hermitian or self-adjoint elements in any one of these three matrix algebras. And more explicitly, that case is realized physically if time reversal exchanges isotypic components, different ones. And these two come when the time reversal stabilizes isotypic component and squares to +1 or to -1. So, with that said, I can now look at, briefly summarize what we did with Peter and Alan. We took Dyson's setting, but replaced the Hilbert space that was fundamental in this case by Fock space. Fock space is a physics word for the exterior algebra of a Hilbert space, and it's physically important because that is the type of Hilbert space that is needed to do physics for many fermions, many electrons in particular. So we had an arbitrary group of unitary symmetries, and then anti-unitaries were also possible, and the well-known time reversal symmetry could be there or could be absent, but the novel feature, highlighted here in red, was that we allowed for a second type of anti-unitary operation, which we called, this is neutral Alan, and we said mixing, a mixing symmetry. I later decided it's better in communication to my physics colleagues to rename it to particle hole symmetry. So the mixing refers to changing the type from particle from a particle being there to a particle being absent, particle hole. It's something that you can write when you are in Fock space, and here is its main characteristic. If half means, so let V be finite dimensional, and half let be half the dimension of V. So we are in the middle of this graded structure. Applying C to a vector that has an excess of Q charges, what you get is something that has a deficit of Q charges. So Q extra particles become Q missing particles. No? So that's why it's called particle hole transformation. In particular, the vacuum degree 0 subspace is mapped to the top degree subspace, and the half degree is mapped to itself. So
V is infinite dimension.
Well,
because then this becomes.
then this I can't do this. Yeah. So
no, I think you can, because there is this
I will elaborate on that difference in a moment. Right now, for this, you should think V finite dimensional. We let it become infinite dimensional in a second. So what did we do? Well, we carried out the Dyson program of classifying Hamiltonians, not in the general interacting situation, but for so-called the so-called Hartree-Fock over mean field approximation, where the Hamiltonians are quadratic in particle creation and particle annihilation operators. And that simplification allowed us to abandon Fock space and push the analysis down to Nambu space, the space of fields in physical language. And then we did the step of reduction by the unitary symmetries, and afterwards dealt with the extra structure coming from time reversal and mixing symmetry. And we found that after reduction, there were 10 types of block data that could possibly arise, and that every one of them does arise, and they are in bijection with the classical irreducible, with the large families of classical irreducible symmetric spaces. This was our paper, and Alan's complaint was, this is relatively simple linear algebra. Of course, he's right. My response was, yes, but it's useful linear algebra. And I feel somehow confirmed in my optimism. Although our work was intended to describe disordered systems, that this is where the motivation comes from, it's found numerous applications for clean systems without disorder, with translation invariance, where you have Fourier block theory at your disposal, and doing Fourier block, you get monospace Hamiltonian momentum space. And one important corollary of our theorem is that there's 10 types of Fourier block Hamiltonians. And this is something that's quite appreciated by the community working on topological insulators and things like this. And indeed, our paper now has close to 100 citations. People find that useful. It should have a lot more citations. Unfortunately, most of them go to that paper, but the real work was not done. So my physics colleagues are either lazy and just cite the old work rather than reading this one, but some of them, I think, try to read our paper and just can't understand it, I feel. So they cite this. So it's the, that's what we did in this SFB. We tried to establish dialogue, get communication going between mathematics and physics. I think we had a certain amount of success, but the problem persists. How is mathematics going to speak to physics in the world at large, and how do physicists understand mathematics? It remains a challenge. I think we helped a little with the situation, but it remains non-trivial. Now, here's one thing that I wanted to communicate. These gentlemen came up with what they would claim is a simpler proof than ours. And it's modeled after Dyson's proof. In that proof, everything is done over the real numbers. So we did not do that, and I'm glad we didn't, because in quantum mechanics, the way we practice it, we do want to be over C. But if you only want to see the number 10 come out, then there is a shortcut. It goes like this. We now have time reversal. We also have this part-over mixing symmetry. And one needs to introduce a notion of twisted G representation, incorporating the T and the C action. And then you do the same thing before, but everything over the real numbers. And then you make the observation that the Hamiltonians, which are built from G equivariant homomorphisms from here to there, if you look at them between irreducibles, they are intertwiners. And before, in the earlier case, there were elements of a real division algebra. Now they are elements of a real superdivision algebra. So the algebra is, say, group graded. There's an even part and an odd part. And then the usual rules of superalgebra.
So these are, what do you call it, rather division superalgebra, you know, superdivision algebra.
Yeah, that's the language of Greg Moore. I agree. Division superalgebra. Yeah. What here is a definition. The division here means that any homogeneous element, so that there are the general elements, there are elements that are not zero, which don't have an inverse. The statement is that every homogeneous element that is not zero has an inverse. So that's what's meant. And it's known that there exist 10 of these. You know, so the non-super ones we've seen before, CR and the fermions, but there's 7 more. There's the Clifford algebra with 1 generator complex. And then there are 3 real Clifford algebras with 1, 2, 3 positive or 1, 2, 3 negative generators. These are the 10 real division superalgebras, and they give you a shortcut to what's magic about 10. It's not constructive. It's sort of like an existence proof, or what are the possibilities. What's better in our work is that by going through this process of reduction and transferring structure, we get the answer. So it's a machine. You put in the physical input, and out comes the decomposition and the types that occur in a physical system. This is not given to you here. So, but if you only want 10, that's the
yeah, and you want 10 because of this sacredness of 10 in whatever, right? And 26 and 10, right? Because I didn't notice before you said 10, but it's that.
Well, there's many ways of making 10 sacred. So it's the dimension where superstrings work. So this is this is not 10.
That or not?
No.
No, it's just.
It's a little bit of a mystery. So there are 10 families of classical irreducible symmetric spaces and 10 associative division superalgebras. And Greg Moore says there's a deep reason why 10 equals 10. 2 approaches classifying the same thing lead to 10 types. So that must be, maybe there's some direct relation. If there's not, the relation is that they come from the same classification problem, and applying different methods, both of them have to give 10. Okay, how much time do I have left?
Well, we have a clock here, so it's easy. I think you have half an hour.
Okay.
From what I see, a little more than.
All right. So this is in red, because that's Alan. There's another reason for red, and that is it's controversial. The community has not really embraced this. The physics community uses particle Hall for something else. I'm unhappy about it. And there's something else. Ed Witten has stated very apodictically that there's only one anti-unitary symmetry, and that's time reversal. And he's right. In relativistic quantum field theory, where you have the Lorentz group, such things, there is only one anti-unitary, and that's time reversal. The other one that you might think is anti-unitary charge conjugation is unitary. Yeah? So Ed Witten is right. When the object of study is relativistic quantum field theory, but I work in condensed matter physics, and different game. And the assertion is, in the physics that we find interesting, what is space for a second anti-unitary, our mixing symmetry or particle Hall symmetry. So the rest of the talk is to throw some light on that, give examples, and tell you about the mathematical structure. In particular, finite dimensional, the infinite dimensional, that kind of thing. Okay, so some examples. First example, the cosine band. Simplest thing one can do is have a particle hop in one dimension, translation invariance, then the dispersion is a cosine. The energy as a function of wave number is this, so it's plotted like this. And now we want to put the chemical potential at half filling, so cut this symmetrically, so that half of the available states below the chemical potential, so in the ground state, they will be occupied. An electron will fill these states, while the ones above the chemical potential are empty, full and empty. And now the particle hole symmetry transformation, C, which is originally defined on Fock space, induces an action on creation and annihilation operators. That's what these A daggers are. A dagger creates a particle, A without dagger annihilates a particle. So there's an operation converting a creation operator for particle momentum K into an annihilation operator at K plus pi. It's shown here. That is a symmetry. That operation leaves the Hamiltonian invariant. It doesn't anti-commute with it, like many installations of particle hole symmetry anti-commute somehow. This is what I disapprove of. This is a good use of the terminology of symmetry. Operation commutes with the Hamiltonian. Very important, it is complex antilinear. Second example. So this was a very simple example. 3 electrons hopping along a chain. It doesn't get any simpler. You can put in interactions. Something called the Hubbard model is pretty much the same thing as before, but now with spin and a half, and then interaction, a local charge interaction. The particle hole transformation sends creation operator to annihilation operator. I'm writing here now in real space and not in momentum space. So instead of the momentum shift, there's now a staggered sign. Nothing happening on even sides and the sign change on odd sides. That's a symmetry because the charge operator is sent to its negative by the particle hole transformation. And this one, it sends this term to its Hermitian conjugate. So the Hubbard model at half Willem is particle hole symmetric. My physics colleagues know that in the limit of sending the Hubbard interaction, which is repulsive, to very large values, ultimately infinity, this problem reduces to an antiferromagnetic quantum spin chain, and so as a corollary one has that the so-called Heisenberg antiferromagnet is particle hole symmetric. We'll get back to that later on. Third example, Dirac field, Dirac fermions. Initially, a Dirac operator, it's called first quantization, is just an operator on an L2 space. The mass of the particle, the speed of light, the momentum operator, and then certain things called beta and gamma, which are the generators of a Clifford algebra, so that this thing, when you square it, gives you the Laplacian. That was the idea of Dirac, to take the square root of the Laplacian, and that led him to consider what's now known as the Dirac operator. This thing has the property that there exists K, which is antilinear, and you multiply with some combination with one of the, in the standard realization used in physics, it's one of these alpha, so-called gamma matrices. So in short, there is an operation called charge conjugation, which is antilinear, and it's not a symmetry of the Dirac operator. It inverts the sign of this thing. So it maps an eigenstate of positive energy state to an eigenstate of negative energy. So it maps electron states to positron states. So it's not a symmetry. However, if one now goes to second quantization, one has to do something. This Dirac operator is not bounded from above, nor is it bound from below. It's not a good model of physics. To get a good model, and get a bounded operator, one has to do some trickery. It's called filling the infinite sea of negative energy states. So you redefine the vacuum. And then the outcome is an operation which is derived from this called charge conjugation, which is unitary. It maps electrons to positrons, like here. It does not do anything to the momentum, it does nothing to the spin, it just changes the charge of the electron to the charge of the positron. And it is unitary, complex linear. It's very confusing. I talked to my physics colleagues and some of them haven't really appreciated this. They stare at me and start asking a lot of questions. That's the way it is. Between first quantization and second quantization, something happens. And we'll now look at it in more detail. So I gave you a few examples. More examples exist, and some will be mentioned later on. So here's some theory. And we'll start with the infinite dimensional case, or a setting where we can accommodate infinite dimension with ease. Notation as before, mu is the chemical potential. We want to speak about insulators here, so the chemical potential should be located at an energy where the energy spectrum has a gap. There should be one spectrum up here and spectrum down here, but no spectrum, no eigenvalues in this gap, and that's where we put the chemical potentials. That splits the Hilbert space into a V plus, the positive energy states, and V minus, the negative energy states. And in the ground state, the negative energy states will be filled, the positive energy states are empty, and to get excitations, we can do one of two things. We can add a particle in the positive energy sector, or we can remove a particle or create a hole in the negative energy sector. So the Fock space, tailored to this situation, is an exterior algebra generated by the Hilbert space, the positive sector of the Hilbert space, and the dual, because we are removing particles to get excitations, the dual of the negative energy space. So that's the Fock space.
Is it an honest exterior? It means honest exterior algebra or something more complicated? No semi-infinite things, just degree one.
At the moment, it's just, and then you want to complete this to Hilbert space by L2. Yeah? But so that's a perfect mathematical object. That's the Fock space of quantum field theory, you know? Because this could be the Dirac field with mass. Mu could be 0. It could just be in the setting of before. This, the one I'm talking about here. Yeah? But it's more flexible, and I want to think about it as a mathematical model for an insulator in some condensed matter system. Now, because V is a Hilbert space, we have the Fréchet-Ries isomorphism, which is complex antilinear and takes us from V to V dual, or V plus to V plus dual, same for minus. In physics, one speaks of the Dirac Keck to bra bijection. You can ignore this. The slides were not tailor-made for this audience. I used some slides of the previous slide. So, what can we do? Assume there is some isomorphism exchanging V plus and V minus. Then you can do a two-step map. In the first step, you let K act on F in the obvious way, exchanging these two factors. That takes you to another Fock space, different from the original one. And we return to this Fock space by applying Fréchet-Ries. In the first step, plus and minus are exchanged. In the second step, we interchange space and dual space, and so we go back to F. This is a two-step process, And we call this a particle hole symmetry if this total operation commutes with the Hamiltonian. So this thing always exists as a particle hole transformation, and then if it commutes with the Hamiltonian, we call it a particle hole symmetry. Important remark, because this two-step process involves and must involve gamma, the Fréchet-Ries, which is complex antilinear, you have this phenomenon that if K, the operation given in first quantization or at the single particle Hilbert space, if that is linear, then you wind up with C being antilinear. That's the case for the Dirac field. That's the case for the cosine band of earlier. There, K was this momentum shift, pi, and then secretly, but now I'm bringing out into the open, gamma is involved, and so C winds up being antilinear. Compare this to the case of the Dirac fermion. There, K was antilinear, and I'm composing it with this, it becomes linear. So that, if anybody was ever confused about this, that's the resolution of the confusion. Particle hole conjugation is a two-step process. There is a map on the single particle Hilbert space, but to get the true map that you want to work with on the Fock space and then on the space of fields, you have to compose it with Fréchet-Ries, and that changes linear to antilinear and antilinear to linear. Now, let's go, this was systems with a gap, you know? And we put the chemical potential in the gap, and then we have an obvious decomposition into V plus and V minus. Now let's think about systems without gap. In that case, we have zero modes, and the full decomposition has to involve a third space, the space of zero modes. For simplicity, the following I will assume that this has finite, that's actually physically well justified. Take V naught to be a finite dimension, V plus and V minus may be infinite dimension. Now, we want to think about particle hole transformations on the space of zero modes. And we define it the following definition. We introduce something called particle hole conjugation. Before I was talking about particle hole symmetry and particle hole transformation. Now I give a short definition of something called particle hole conjugation. That's a tautology. It's the tautology, which is given as follows. It's the antilinear algebra automorphism, which exchanges creation operators with annihilation operators. Now here, I remind you of what these things are. Creation operator, that's exterior multiplication with a vector in Hilbert space, that creates a particle. The annihilation operator is inner contraction with a dual vector, covector. And so, particle hole conjugation is the antilinear algebra automorphism that exchanges A's and A daggers. We now ask, does this thing defined at the operator level, does that lift Fock space? The answer is, does there exist a lift, I call it psi, a lift that maps the n particle subspace of the space of Fock space of the zero mode to the capital N minus little n. Capital N is the dimension of the subspace of zero modes. The answer is yes, and it goes as follows. Remember, we have, by the Hilbert space structure, we have the Fréchet-Ries isomorphism sending a Hilbert vector to the corresponding covector by inserting the vector into the part of the Hermitian inner product which has the complex conjugation. And that, of course, induces an operation on Fock space, just doing it factor by factor. And since V now is finite dimensional, we can identify this, the wedge n of the dual, we can identify it with the wedge ND dualized. Now we need something else, and that is obtained as follows. We fix a generator in the, physically speaking, totally occupied state. Take the maximal degree that's allowed by our capital n-dimensional space of zero nodes. And having made such a choice, we introduce what I call a wedge isomorphism. That will be a map that acts here and outputs something in wedge capital N minus n. How does it go? Well, you wedge it with a test state, test form, test vector, and so this has degree little n. The test vector is, well, this takes you here, so to wind up in total degree capital N, you should wedge with a little n particle state. And then you apply the duality pairing covector with vector, and so that equality defines this omega sub n. And then for maximal beauty of following formulas, you do some alternation on signs. And particle Rho conjugation now is again a composite. You do the Fréchet-Ries on Fock space in the first step, and then you apply this wedge isomorphism. It's complex antilinear, and my physics audience usually is lost at this point, and then I help them by saying, listen, if you work this thing out in the so-called occupation number basis, where every single particle state is either empty or full, then the effect of psi is very simple. Every occupied state becomes unoccupied, and every unoccupied state becomes occupied. It doesn't get any simpler. But one can put it in fancy math that maybe is not clear to everyone. Now, if this rings a bell and you say, well, I've seen this before and it's called the Hodge star operator, yes, this is Hodge star. There's a slight difference. Hodge star, we usually meet it in the real setting. No complex numbers needed. We do Riemannian geometry, differential forms, and then there's a Hodge star operator determined by the Riemannian geometry. There are no complex numbers around. This is very similar, but instead of the metric tensor defining the Riemannian geometry, we have the Hermitian scalar product of quantum mechanics. Other than that, it's the same thing. So particle Rho conjugation is a complex variant of the Hodge star operator. And here's a few facts about it. If X is a one-body operator, so something quadratic in creation and annihilation operators, and it is self-adjoint, and it's Weil ordered, that means it's a physics word for skew symmetrized, like here. Then such a thing is always odd under particle Rho conjugation. It has this property. It's easy to show. And now comes an important remark, which will play a role at the end of the talk. The remark is particle Rho conjugation can never be a symmetry. And that's clear from here. It cannot be ever a symmetry of what's called a Fermi-liquid or any kind of simple ground state because of this swapping of occupancy to emptiness. If you have some simple state where you fill a Fermi C and you particle conjugate, you sort of empty out the Fermi C and you populate the states above. So that could never be an operation that transforms a ground state into itself. So it could be a symmetry of the Hamiltonian, but it can never be something that transforms the ground state into itself. You have a question?
Yes, so ordinary Hodge star maps harmonic forms to harmonic forms. Does something like this happen here too?
Yeah, harmonic means there has to be a Laplacian. The harmonic forms are the ones annihilated by a Laplacian. I don't know. It's not immediately relevant. It becomes relevant but once you ask such a question. I'll think about it.
Yeah, but you were talking about this thing being a symmetry, so that's why.
Yeah. Okay, so again, psi can never be a symmetry. Let me skip this and now finish the talk with an attempt to communicate two messages. The following slides are a lot of physics, and I don't want to do this to you. But there are two messages, and I'll make an attempt to get them across. Now, the first message is our work with Peter and Alan was motivated by distributed systems, and then we heard it found applications in systems with translation symmetry without disorder. That's one thing. But the other thing is it is now finding applications also in interacting systems. Our work was on non-interacting, quadratic Hamiltonians. The technical simplification from that was that we could push things down from Fock space to the Nambu space of fields and analyze things there. To do interacting systems, one has no choice but to work on the Fock space. And what's important to me is that we set things up right. We set things up in the Fock space, the definition of the symmetries. And so the things that we did and the classification that we obtained continues to make sense in the interacting world. And that's a much bigger world. It's the world that most physicists find to be the interesting world. The world of free fermions, well, this is a nice thing. You can do some exact solutions. You can, but the real world is interacting. So the first good news is that what we did also gives guidance and classification in the interacting world. Here's one example to underpin this statement. And now the question is how to walk you through this. It can be sold as something about recent Nobel Prize given to Duncan Haldane, 2016. What was honored here was work on antiferromagnetic quantum spin chains. So chain means we are in one dimension. There's a chain of spinning degrees of freedom. Antiferromagnetic character is that one spins one way and the neighbor spins the opposite way and the next one again spins the opposite way. This alternating feature of the spinning motion comes from this Hamiltonian, which has positive J. So he wants the spins to have the lowest energy, he wants the spins to be opposite to each other. The circulation should be like here. So Haldane figured out something about these chains. Let me jump to the thing that is most striking, and that is that there is some sort of topological order in this chain. Certainly for this, it depends on the Hamiltonian, but this simple Hamiltonian, the Heisenberg Hamiltonian, does the job. There's something very interesting about it. If you consider that chain with periodic boundary conditions, or with open boundary conditions and infinite length, then you find that it has a unique ground state, unique translation invariant ground state, and with a gap for excitation. So if you want to excite the system, you have to put in a minimum amount of energy. This is what Haldane found out. But more interestingly, it turns out that if you consider that chain with finite length, then at large but finite length, then near the boundary where the chain begins or ends, you have so-called zero modes. There's the possibility of exciting this antiferromagnetic chain by a mode that costs no energy. So zero modes, and these zero modes do something very peculiar. Although the spins are integer spins, one has fractionalization. So these modes at the end have spin a half. That's very peculiar, and the physicists find it fascinating. So it's a new paradigm in the world of correlated systems and fractionalization. Now, when you have such a feature that some zero modes appear at the boundary, physicists ask, well, how robust is that? Will these things always be there? If they're always there, and we'll build a quantum computer with it, because it's somehow protected from dephasing, things that destroy quantum coherence and that obstruct the functionality of the quantum computer. So physicists get very interested in these zero modes. The question is, how robust is it? Is this thing always there, or does it go away? And the answer is, well, it's not so robust. Some symmetry has to be obeyed. So it's a symmetry protected zero mode. And the holding phase where this happens is called a symmetry protected topological phase. But now, what symmetry? Well, that was a debate. The initial answer was time reversal protects, and some other things do. Then my colleague Achim Roche in Cologne came and pointed out that if you enlarge the Hilbert space, if you allow, so these spins are physically made from electrons. There's no such thing as an abstract spin. The spin comes from electrons. And if you want to have spin 1, there have got to be 2 electrons lined up, 2 spin-a-half electrons making spin 1. So there are electrons, and in order for the spins to couple, the electrons have to move. It's called antiferromagnetic exchange. So the physics actually says there are electrons, and actually they move, charge fluctuates. So when you allow charge fluctuations, Roche shows that the protection does not take place. You can deform the Haldane phase to the symmetry phase. So bad news. So then people thought about it, and so time reversal does not protect. And then Pollmann had an idea that some reflection symmetry, reflection at a bond, protects. But this does not explain why the Haldane phase would be robust with respect to this order. Then I had the idea that what protects is particle symmetry. So that's why this is part of this talk. It's one of the applications of the concept of particle symmetry. And in the meantime, this actually has been published and shown by Pollmann and others. And maybe this is the only thing I will say more about this. Let's have a statement. We say that 2 Hamiltonians, so there's 2 parts of the statement. First, we have to define topological phase. 2 Hamiltonians said to be in the same topological phase, so a topological equivalent. If there's a homotopy, the parameter t, it starts at one and ends at the other, such that along the path of the homotopy, the Hamiltonian always has a unique ground state. There's no degeneracy ever. And the energy gap stays open. The unique ground state must always be separated from the existations by a minimal energy gap which is not allowed to go to 0. If that's the case, we say that H0 and H1 are in the same phase. Second definition, we say that the Hamiltonian is of symmetry class A3. That refers to our classification and the Cartan terminology of it. If it commutes with charge, so it conserves charge, and it commutes with a particle-hole transformation. The statement then, the claim that I made, and claim has been verified, is that with that definition, the holding phase is connected by, its topological equivalent is connected by homotopy with a free fermion phase, with something that falls into the class of things that we looked at and classified. So I'm very happy about this, because it means that our classification work, which was done for free fermions, extends into interacting domain, and it does not capture everything that's out there. In particular, fractional quantum Hall states are not in the picture, but the holding phase is. So I think that's beautiful, and I like to advertise it. That was message one, and there's a lot of physics that I will not hit you with. So the final message is to go back to the beginning of the talk. Remember, I spoke about quantum Hall effect, lowest Landau level. The math for this was holomorphic sections of a complex line bundle. And now we go to half filling. So we have a certain number of states given by these holomorphic sections, and we put electrons in there by gating, by doing what people do in the lab, and filling in half the available states. So that's half filling, and then particle-hole conjugation transforms half filling into half filling, and there's a possibility for a ground state that might be particle-hole symmetry. Many years ago, and then that's, you can see that from the experimental data. I'll show them, flash them again in a second. I didn't point it out earlier. That state at half filling is not an insulator. It has massless excitations or gapless excitations. 25 years ago, some colleagues made a proposal how one could understand these massless, this massless feature. But, so there's a lot of physics that I again don't want to explain to you. But what I want to highlight is that that old theory does not talk at all about particle hole. It just ignores it. And recently this came up. The old theory was criticized, and there's now a new theory which is particle hole symmetric. And in pictures, the cartoon describing these low energy excitations, which are called composite fermions, is like this. You imagine inserting two flux quanta in the plane. That process pushes away one charge. It creates a charge deficit of minus an electron charge, and then that charge deficit binds one electron. And this whole thing is called a composite fermion, and that was the traditional view of Halperin Lee-Reed. Now, Son wants to modify this and produce a particle hole symmetric picture. Right? In the first instance, this sounds crazy. Remember, so the symmetry that the system has is, well, what's there is particle hole conjugation. And we argued earlier that this can never be a symmetry of a Fermi-liquid ground state. Yet Son wants to make it a symmetry. So this seems like an impossibility. So something has to give. And what has to give is you have to change the degrees of freedom in which you're working. If you want to do things in terms of the original electron degrees of freedom, no go. It's not possible to have particle conjugation and symmetry. But so Son says we need to change the description. Instead of electrons as or Dirac fermions as the fundamental degrees of freedom, we want to turn to a fermionic vortex field, whatever that is. And again, too much physics to explain here. That there's one thing I want to highlight in that dual. So first of all, this duality transform is something accepted by physicists. The best people, including Seiberg and Witten, have worked on this and have given their approval. So this transformation from electron degrees of freedom to fermionic vortex is accepted. There's no mathematical theorem, but theoretical physicists have made up their minds that this is a good transformation. And now something very bizarre happens. I was shocked when I first saw this. In this dual representation, the time reversal in first quantization is complex linear. And it anti-commutes with the Hamiltonian. So, the Hamiltonian is odd, always odd under charge conjugation. That's nothing new. But the Hamiltonian here is odd under time reversal and odd under period. That's reflection at a line in the plane. Time reversal is complex linear. Reflection at an axis is complex antilinear. That's totally bizarre. I had never seen such a thing in my life before. It all gets fixed by understanding that the first quantized theory is only the first step. You want to transform this into by field quantization or second quantization into the theory on Fock space, bringing in free series and blah, 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 as I tried to show, and then everything is fixed up. In the final version, time reversal commutes with the Hamiltonian in respect to antilinear. And what it does for you is that if you take C and so the relativistic charge conjugation and time reversal together, that is complex antilinear, and it is the way particle-Hall conjugation is realized in this dual theory. Pictorially, this is the interpretation of Sonworks by Wang and Sentel. The old picture of the composite fermion due to Hauptmann and Reilly is replaced by a new picture. In the new picture, the two flux quanta are considered separate, and one insertion of flux creates a charge deficit of -1/2, the other one binds an electron so that you have this dipole now. As before, the whole thing is electrically neutral. The charges add up to 0, but it has a dipole moment. And this one now is particle-Hall conjugation symmetric. If you exchange the charges and then correspondingly reverse the dipole moment, pointing from one to the other, then, as you can see, that's the same thing as a rotation. You know? So, in the original electron degrees of freedom, particle-Hall conjugation cannot transforms a charge into a Hall, and it could never be a symmetry of a ground state. But when it acts on these composite objects, it's just like a rotation. So now particle conjugation can be a symmetry of a Fermi sea formed from these effective degrees of freedom. Fantastic story. I was blown over when I first saw this, and it's where I want to finish. Thank you, Alan, for the years that we spent together, and we did some useful stuff. And the point of this talk was to let you know that it was not a waste of time. Our physics colleagues, some of them at least, appreciate what we did. And I wish you all the best for your further papers here in Bremen and elsewhere. And all the best also to Barbara, who's been listening to this in the background. Thank you.
The vocal people are running.
Yeah,
But it's been great. Thanks so much. Thanks, Ivan and Kayvon.
Alles Gute, alles Gute.